Hi, welcome to Are YouTube Views Poisson Distributed? Okay, so the Poisson distribution and its importance and its utility is a common theme that shows up on this channel. In the video Why the Poisson Distribution is Important, It's Everywhere, we looked at the Poisson distribution in a few cases. For example, radioactive decay, holes in one at a golf course, failure rates of components, etc. Now, the Poisson distribution is relevant when some event has a constant probability of happening per unit time. So, for example, we could have a radioactive sample that has, on average, lambda decays per minute. The Poisson distribution, which we write as P of m given lambda, tells us the probability of having m decays happen in a given 1-minute interval. So here's the question that we're going to ask in this video. How about the daily number of views on a YouTube channel? So if a channel gets, on average, lambda views per day, is the number of views per day well described by a Poisson distribution? So we'll start by asking whether or not we should expect the channel views to follow a Poisson distribution. And then after that, we'll look at some data from Think Like a Physicist's channel analytics. And the goal is that this will demonstrate some of the considerations that might go into concluding whether or not you expect some quantity to be well described by a Poisson distribution. So we'll take a look at the daily views from 2 months of Think Like a Physicist. Now, this channel has educational content, and the channel's traffic has some seasonal features which seem to coincide with the school year. And this already tells us that a Poisson distribution won't totally describe the behavior of the views on this channel. But maybe a Poisson distribution will work okay for short time periods. So here we're going to choose a time period when school isn't starting or ending, and we're also going to look at a short time period over which long-term trends might not have very large effects. So okay, here's the plot of the views for Think Like a Physicist from October and November of 2020. During this time, the channel averaged 52.95 views per day. Okay, with that, let's go over a quick review of the Poisson distribution. So let's say we have some event which occurs randomly, whose probability of occurring per unit time is constant, and where the occurrences of the event are independent. So the rate of the event occurring per unit time is independent of how many times the event has occurred before or when it occurred before. So let's call this rate R. So for example, the event could happen on average 3.2 times per second, 457 times per year, etc. On average, over a time interval t, the event will occur RT times. Now, if we're given a specific interval t, the probability for the event to occur in actuality m times is the Poisson distribution. So we write this as P of m given RT, and it is equal to RT to the power of m, e to the minus RT divided by m factorial. And we also sometimes define this term lambda, which is equal to RT, and we write the Poisson distribution as P of m given lambda, which is equal to lambda to the m, e to the minus lambda, divided by m factorial. And it's this latter notation that we'll be using in this video. Okay, so here we're going to look at a time interval of 1 day. And we're going to compare actual YouTube videos with a Poisson distribution where RT, or lambda, is equal to 52.95 views per day. And so in this case, the probability of actually observing m views per day, if the views are determined by a Poisson distribution, with an average number of views per day of 52.95 is given by 52.95 raised to the power of m, e to the minus 52.95, divided by m factorial. Okay, so now let's ask the following question. Should we expect the Poisson distribution to apply to YouTube views? Well, alternatively, let's ask the question, why might we expect daily views to not be Poisson? So the Poisson distribution assumes the following. It assumes that lambda is equal to 52.95 views per day, and that this does not change with time. And it also requires that the individual views be independent. So are these conditions fulfilled by YouTube views? So first, let's look at some reasons why we might not expect lambda, which here we've set to 52.95 views per day, to actually be constant in time. So, as we've said before, the channel views do seem to be correlated to the school calendar, and so this leads to some questions. So, might there be a slowdown in the channel traffic on holidays? Might there be more views during final or midterm exams? And should we expect there to be a dependence on the day of the week, say comparing Monday versus Saturday? We can also ask a few more questions. For example, might there be more views on average on days when a new video is uploaded? Might there be long-term trends in the traffic to the channel? Might there be changes to the YouTube algorithm that changes the traffic to the channel? And also, the fact that we needed to choose a time range during the school semester when school wasn't starting or ending already indicates that there's some time dependence that isn't summarized by lambda being a constant. Okay, now let's look at some reasons to suspect that the views are not actually independent of each other. So viewers often click on more than one video from the same channel during a single viewing session. And also, if someone likes a video, they might share it with other people who then click on it. So therefore, we might expect that on some days, people are either more or less likely to click on the videos, and so constant lambda is likely not a very good approximation. And we might also expect that views will come in clusters. So here's a hypothesis. We should expect more days with very few views or very many views compared to the expectation of a Poisson distribution. So let's see if that hypothesis pans out. Okay, so now let's compare those 2 months of YouTube views to what we would expect from a Poisson distribution. Okay, so here we show a plot of the daily number of views. So the x-axis has the number of views, and the y-axis is the number of days on which the channel had that number of views. So for example, there was one day that had 132 views, and there were 4 days that had 56 views each. So now let's compare that to the expectation we would get from a Poisson distribution with lambda set to 52.95. So a Poisson distribution gives us the probability that on any given day we'll see a certain number of views. So if we want to get the average expected number of days that will have that number of views, we take the Poisson distribution and multiply that by the number of days, which in this case is 61. So that is shown by the black curve. Now we can see that the distribution of the data from the YouTube analytics, shown in blue, looks wider than the Poisson distribution, shown in black. In particular, there were 4 days that had large numbers of views that would be very unlikely if the views were in fact Poisson distributed. So for example, we can look at that one day that had 132 views. If the views followed a Poisson distribution with lambda equal to 52.95, the probability of getting 132 views on a given day is 3 times 10 to the minus 20. And we did have 61 days of data, but nonetheless, this is an extremely rare event. We could have asked for the probability of getting 132 or more views on a given day, but that would change the probability that we just quoted only by a factor of order 1. Okay, so next let's look at the day that had the next highest number of views, which was 101. So if the views were in fact following a Poisson distribution, the probability of having 101 views on any specific given day is 1.4 times 10 to the minus 9. So even though we've looked at 61 days of data, this would still be a remarkably rare event. Okay, so we looked at a couple of days that had anomalously large numbers of views. Now let's look at a day that didn't have that many views. So there was one day that only had 27 views. So the probability, if the views really were Poisson distributed, of a specific day having 27 views is only 3 times 10 to the minus 5. Now this is a small number, but it's actually not that small. So given that there were 61 days of data, the probability of there being one day with 27 views is 3 times 10 to the minus 5 times 61, which is actually 0.2%. So that's not terribly rare, but on the other hand, it's also not that common. Okay, so we've seen that there are more outlier data points than what would be expected from a Poisson distribution. But we can also see this in a more quantitative way. So we can compute the standard deviation sigma of both of these distributions. In the case of the Poisson distribution, sigma is given by the square root of lambda, which here is the square root of 52.95, and that's about 7.3. On the other hand, we can calculate the standard deviation of the YouTube view data, and we actually get that it's 17.3, substantially larger. So the data distribution is substantially wider than what would be expected from a Poisson distribution. But I want to emphasize that this is not just driven by the outlier data points. So if we removed the 4 data points on the high side of this distribution and the lowest point on this distribution by hand, we would still get that the standard deviation of the data distribution was 10.3. So the main chunk of this distribution is still wider than what we would expect from a Poisson. Now it can be tricky to compare the theoretical Poisson curve to our YouTube analytics data by eye. So let's compare our YouTube analytics data to some simulated data. So here, our YouTube view data distribution that we've been looking at is in blue in the top left, and the other 8 plots are simulated distributions. So here, the simulated distributions assumed that the views were Poisson distributed and had lambda of 52.95 and again 61 days of data. And then we made the plot in the same way as we did for the real data. Now the standard deviation sigma of the simulated distributions varied from 6.8 to 8.6 views. So these were all far narrower than the sigma of 17.3 that we saw in the real data. Okay, so now let's turn to a discussion. Okay, so we had some suspicions at the outset that the Poisson distribution might not describe the data all that well. So first, it seemed like a constant lambda was likely not a good approximation to reality, and second, it also seemed like the views would likely be correlated. So it seems reasonable to expect that these effects would cause more days with very many views and more days with very few views than what one would expect from a Poisson distribution. Now, we can see visible differences between the distribution of YouTube views over 61 days and what would be expected from a Poisson distribution. And these differences are in line with the above expectations. So the distribution in actual data is wider than the Poisson expectation, meaning there were more days with lots of views and more days with very few views. So hopefully this illustrates effects that we should keep in mind when we're trying to figure out whether or not we expect some phenomenon to be well described by a Poisson distribution. And we should also keep in mind that these effects can be subtle. Now, we looked at the number of views on Think Like a Physicist in a day. We could have also looked at different time intervals. So for example, if we had looked at time periods shorter than a day, then we might have seen effects like 1, particular times of day typically being more or less active, and 2, clusters of views from individual viewers looking at multiple videos. Okay, so let's briefly summarize. So here we looked at 2 months of daily views on Think Like a Physicist to see if they looked Poisson distributed. There were reasons at the outset to suspect that they wouldn't be well described by a Poisson distribution. The distribution of views showed deviations from a Poisson distribution in the direction expected from our suspicions. So basically the distribution was wider than what we would get if the views were Poisson distributed. And hopefully this illustrates tricky things that we need to watch out for when trying to figure out if some phenomenon might be approximately Poisson distributed.